Our next set of things is 4 through 6. So we'll talk first about the positive test charge placed at the location of the black dot in question 2. Accelerates from rest. What is true about the signs of kinetic energy, potential energy, and net work done by the electric field? So just to remind you, question 2, that was this one. So it was we have a dot here and a plus and a minus charge. So let me just redraw that. So I have a plus Q here and a minus Q here, and we are putting a small positive charge, a small positive probably test charge right there in the vicinity of these two source charges. So the answer to this question is pretty much independent of this reference to question 2. I gave it to you as something to kind of look and think about because you already figured out that the electric field here points to the left. So if we place a positive charge at that location, the positive charge will want to go to the left. But the real important thing here is this part of this question that says that it accelerates from rest. So we're letting this positive test charge do what it just wants to do. It's not under the influence of any external forces or anything. So this is that we're putting a small test charge on the sheet somewhere. And it doesn't really matter what the shape of the sheet will do. What it is going to tend to do is roll down the hill. And as it rolls down the hill, it's going to speed up. And that means that it's going to increase its kinetic energy. And as it rolls down the hill, its potential energy is going to go down. The work energy theorem connects these two. Net work done by the electric field is equal to the change in kinetic energy. So if that one's greater than 0, that one is greater than 0. These kind of always look this way because we're really not dealing in a spot where we have any non-conservative forces. So as long as we're not kind of doing work on the system, so as long as we're not kind of pushing charges and forcing them to do things that they don't want to do, a positive test charge will always look like that. This would be different if it was a negative test charge, so that's an important thing to look here for. Negative test charges do the opposite of what you would want to think. So negative test charges will speed up as they roll up the hill. So all of these circles would be the other, none of them would be 0, but if it was a negative test charge, then I would instead circle that one, and that one. All right, so the next question is what's the correct representation created by two positive test charges? So we know the electric field points away from positive test charges, so that's what we're looking for. Down here they point away, and down pointing away. And here they're pointing away, but down here they're pointing toward, which is not what electric field lines should do. So that's not going away from the positive test charge everywhere, so that can't be it. Away and away, so we're good up there. Away, and then right here, those arrows are coming in, so that is toward. So that is also not the correct answer. With C, we have all of these arrows pointing away, and all of those arrows pointing away. So that's probably our right answer, but we'll check on D just to make sure. And in D, we have all of the arrows pointing in. So neither of those would work. So the answer there is C. Question 6 is a capacitor that is attached to a battery. And this could be worded more clearly. But it's just a question that I pulled from either recitation or lecture earlier. If this were a test question, I would word it more clearly. But what I mean for you to interpret here is that a capacitor is attached to the battery, and with the battery still attached, the plates are pulled apart. And that means that the distance between the two plates becomes larger. So these types of questions always have the charge is capacitance times voltage equation at their heart. And there's 3 variables in here, and one of them will always be the same. So because this capacitor stays connected to its battery, if it's connected to a 9-volt battery, that means that one plate will be 0 volts and one plate will be 9 volts. The voltage there will always stay the same, no matter what. So that is the thing that we know stays the same. And then the question is to try to figure out whether both of these go up or whether both of these go down. And so we can't just necessarily reason that from this equation, so we need another equation. I don't have my equation sheet right in front of me, so I don't remember the exact equation. Let me get it pulled up, actually. There it is. So there's an equation on your equation sheet under the parallel plate capacitor section that says that the capacitance of a capacitor, remember that is always a property of the capacitor, it's not going to change unless you actually change the configuration of the capacitor. But that's exactly what we're doing here, is we are changing the distance between the 2 plates. So even without an equation, if you sort of logic this out, capacitance is defined to be the ability to store charge. So if you pull the plates apart, I would expect that maybe they have less ability to store charge. Those 2 plates have less influence on each other. If you look at the equations, that's exactly what you see does happen. So capacitance depends on, that is the equation there. So it depends on this constant here, which is a dielectric constant. It's 1 for air, and there won't be any dielectric questions on your final, so you can just assume that that will always be 1. That is a constant that is given on your equation sheet, but basically these 2 numbers here are constants that aren't going to do anything. The only thing that really affects the capacitance of the capacitor is the area of one of the plates and the separation between them. So if we're making the distance get bigger, then the number in the denominator is getting bigger, so this one over here has to be going down. So we know that capacitance is going down, and if the capacitance is going down, then from that equation the charge has to be going down too. So there is what I would answer for both of those.